So I'm going to be talking about this interesting little system, Urbit, that I and some friends have built. Urbit is a clean slate, full stack system. Let me explain sort of briefly the problem that we're solving here first, because this is a little different from the problem that a usual language is solving. So we have basically a coupling of kind of two interesting problems here. We have a very different kind of technical problem that we're solving, and we also have a different human market need that we're solving. So let me go through both of those super quickly. So the technical problem I'm trying to solve here is something I'll call a high-level deterministic computer. So that would be basically a computer whose entire life cycle is defined by a single frozen function. So it's really very functional. Of course, a hardware VM, a CPU, is defined by a single frozen function, which is the CPU function, which is very frozen because it's on the chip. But we'd actually like to define that at a layer at the same level at which the programmer conceives of the system. So if we look at some kind of approximations to this that exist in reality today, JavaScript and the Java VM, of course, are high-level definitions, but they're defined only sort of for a transient system. So here we're defining the whole life cycle of the computer. This is not just a memory image. This is the whole machine, which is a single-level store. Lisp and Smalltalk have these image-based systems that come a little closer to this kind of approach. I don't think people in practice usually use Lisp and Smalltalk actually as databases, and they're not defined, kind of functionally in the same way. But it's definitely in the image-based, system tradition. When you're using this thing, it basically feels like an integrated interpreter, OS, and database, which is a very kind of unusual feeling for a programming environment. You might also ask what happens when a deterministic computer hits an undecidable problem. We'll get into that in a little bit. One way of sort of defining this problem that I like to use is an unusual versioning system that we use, which I call Kelvin versioning. So Kelvin versioning, you count down to absolute zero and you count by integers. So if you run out of numbers, you've made a mistake, basically. So absolute zero is absolutely frozen. So Urbit, or at least the formal definition of Urbit, which does fit on a t-shirt, is at 5 Kelvin, which is like liquid helium, basically at the moment. And we'll see that spec in a little bit. Let's switch gears totally and talk about the human need that this system is supposed to be solving. We have this little problem in the computer world, which is that the internet actually failed. It succeeded very well as a digital modem. It's a great digital modem. It's entirely a client-server environment. It is not a peer-to-peer network. It's never going to be a peer-to-peer network. And if you look at sort of the dream of the internet from the 80s and 90s, it was a dream in which everyone on this network would have their own server, and things like what we do on Facebook today would be done by protocols like SMTP. Well, you can't introduce a new wide area protocol on the internet today. You can barely keep SMTP alive. These systems were designed in the 70s. The same thing for basically Linux, which is, in a sense, I would say, layer 7 of the internet. It's the application layer. Like, if you're on the internet, you're either a Unix box or you're pretending to be a Unix box. You can't really say, I can't really say to my mother, hey, you should go out and get an AWS box and put all your data on that and apt-get install, something. That's just never basically going to fly. And so we've kind of reconciled ourselves to the sort of loss of this dream where people actually control their own individual computing. And instead, we've basically gone back and we've recreated the Hayes modem protocol with HTTP, and we've recreated AOL with Facebook. And we're kind of stuck in this space. So we have a big problem here, and these systems are basically not fixable. Well, there's a way to get out of a problem that isn't fixable, which is to layer over it. So the browser already did this on the client side. Basically, you had these OS APIs, and they're like, okay, we're going to build a new application layer. I guess browser people didn't really realize that this is what they were doing, but it's certainly what they were doing. We're going to build a new programming layer that is isolated from the substrate under it, that cannot call out in any way, shape, or form. And we're just going to program to that layer and not care about the underlying OS. And that actually kind of worked great. So on the server side, basically, this hasn't been done yet. And I would say basically we don't know that people don't want personal servers. People, you ask them, like you tell them what a personal server is, and they say, yes, I want that. We do know that they don't want Linux and internet personal servers. We do know that my mother is never going to run an open, Linux server on the internet. So there's basically a real case to be made for saying, okay, we need a new layer here. If we sort of drill down a little bit and define the need is basically caused by the essentially the obstacle to the universal personal server is just administrative cost. My mother is not a Linux sysadmin. So when you're looking at a problem and your problem is administrative cost, it makes sense that a solution to this problem is going to be technical simplicity, because basically the difficulty of administering the system tends to be roughly proportional to the number of lines of code in it. And if you haven't noticed, there's a lot of lines of code in Ubuntu. So basically, the idea of building the browser for the server side is sort of a problem that kind of makes sense next to this problem of let's build a high-level deterministic computer. So okay, let's build it. How do you define a one-function computer? Well, remember, we're defining both the network and the OS here. We're really, defining a computing environment as if we just stumbled on a planet that had chips and wires and no software whatsoever, which is kind of fun. And if you're going to define the way this works, you're defining networking from scratch. I find the simplest way to think about networking is to imagine just basically a global party line. So a packet is just a big integer blob that people put out. Everybody hears everyone else's packets, and if you have the keys to decrypt those packets and make them make sense, then you use them. Then you can basically say to this global party line, hey, we would like to actually optimize this, and you get back to routing. But routing is basically an optimization in, Van Jacobson has this great term, a content-centric network, where you're basically ignoring who sent you the packet doesn't matter. What matters is what's in the packet. So that's sort of the network perspective on this. From the sort of functional perspective, there's basically two ways to define a one-function computer. You can define it as a lifecycle function, which is where the state is a pure function of input history. And remember, this is a frozen function. This never changes. You cannot upgrade this function. Or you can define it as a transition function, where basically you have an input event in an old state, out comes a bunch of output actions in a new state. These are really, in practice, basically turn into the same thing. In practice, essentially any lifecycle function is going to wind up spending most of its time as a transition function, because you're certainly not going to recompute the whole log every time you get a packet. And one of the advantages of doing it the lifecycle function way is when you're basically building this system where you have one frozen function which defines the semantics of every computer in the world, you need to basically break symmetry, and you need to basically, when you're starting that up, you need some startup packets, you need some startup, you need to load an operating system into your function, essentially. And so a lifecycle function makes slightly more sense as a way to define this. Let me skip down for a second and talk about how you implement these things. Actually, implementing a sort of one-function computer like this is kind of very easy with the kind of substrates that you have at the moment. Event sourcing is basically this pattern. It's usually not used for a general-purpose computer, but it's the same pattern. You have low latency reliable logs are like uniformly available. Kafka isn't the greatest thing in the world, but it works fine. Normal databases are defined in terms of an append-only transaction log and an image snapshot. So you're basically building this the same way a normal database is built. You're saying every packet is a transaction. And it basically works great. You can also do non-packet I/O. I mean, I like to think of an abstract computer as just packets in, packets out. But, as you'll see, we want to serve web pages and so forth. So basically, you can model even ordinary, like HTTP requests as, here's an event that's like, you got a request. Here's my action. Respond to this request. So there's a great library, libuv, which is used by Node.js, that implements these patterns very nicely, so it's super easy to do. I mentioned decidability earlier. That's kind of an interesting problem for a deterministic computer or any kind of non-preemptive OS. When you're building a non-preemptive system, basically the decision of when to terminate a computation is essentially a heuristic choice. If that event is caused by a console, that heuristic choice is very easy. Just go until they hit Control-C. If it's a packet, that's a little harder. You need to decide when to time that out. There's a kind of nice duality between unreliable packet networking and Turing completeness, in that sort of when you drop a packet because it's spending too long, you're essentially detecting congestion in the CPU. And so that kind of makes a certain amount of sense. Node.js has shown that you can actually do very useful things with non-preemptive systems. One of the most interesting problems in building a system like this is you're going to have certain kinds of non-determinism that you can't avoid. Let's say I write an infinite loop. I made a mistake. I wrote an infinite loop. I press Control-C. One thing I really want there is a stack trace. So that stack trace is completely non-deterministic information. You can't, get that in a deterministic way. But all is not lost, because basically your interpreter, the underlying C code that actually implements this system, sees that stack trace, has that stack trace. All it needs to do is basically inject that back in as a deterministic event. And so basically you get an event that says, hey, I was trying to do this packet, but it crashed, and here's where it crashed. And then you can route that to the user in the appropriate way, and that actually works. So if you replay that log, we've replayed like 30 gigabyte logs and wound up for the same bit-for-bit state, right? If you replay that log, it will replay the error. Essentially, it won't even bother with the original transaction. So this is, this is not pie in the sky. This is clearly, this is a working system. This is clearly doable. Probably a lot of Lisp fans in the audience. Let's try doing this in Lisp. So it's actually easy to define a lifecycle function in Lisp. You simply say, okay, the first event in the log is my operating system, and all the rest of the log, the killer of the log, is the rest of the events. So run the operating system on the rest of the events. You still have to write the function, but okay, you've made progress. And now all we need is the one true Lisp. I think all Lisp needs is the one true Lisp. There have been a lot of attempts to create the one true Lisp. They haven't really worked out. In my view, that's basically a problem that goes back to really the root of how we came up with this idea of computing. Because the Lambda calculus is, it's okay, we're at LambdaConf. I can't say bad things about Lambda calculus, but it was originally designed not as a means of programming. It was originally designed as basically a meta-mathematical tool. And people picked this up and they found, hey, wow, this thing that Church came up with actually works like really well for programming. So you take that in one direction and it becomes Lisp. You take that in another direction, much more mathematical, and it becomes Haskell. It's not like Lisp and Haskell are like compatible in any ways. You're always basically taking Lambda and you're growing hair on it to make it a practical system. And I would say that comes from basically a sort of very deep kind of conflict in the heart of Lambda, which is that it has these features that are like symbols and variables and scope that are features of a higher level language. But if you want to use that as an axiomatic system, and we just saw a talk on Shen, which compiles to Lisp, if you want to use that as an axiomatic system, basically, and put the higher level language as something that is actually loaded onto that axiomatic interpreter, then those things are in the wrong place. They're in the wrong layer. And if you're going to build an axiomatic system like this, you have just the demands on the precision of your interpreter are just extremely high. You want that to be just tiny and diamond perfect. And you can't grow hair on it. So in a way, basically, you sort of have no choice but to invent a kind of different computational model at the bottom end. So this, gives me a motivation to actually, invent all this crap. We know that you should never invent anything, but sometimes you have no choice. So the bottom of the stack is this thing called Nock. It's a typeless frozen combinator interpreter, non-lambda. It's defined in 200 words. It fits on a T-shirt. I'm not wearing the T-shirt today, but I'll wear it tomorrow. I know, it's a bad choice. On top of that is Hoon, which is a pure strict type functional language. It compiles itself to Nock. This is type functional programming without category theory. We've heard from some people that they hate category theory. I've heard that somewhere, not sure, probably not in this room. So you can see how if you have a compiler that compiles itself to Nock, then you can kind of bootstrap off of this basic, essentially bootloader. On top of that, we have Arvo, which is a non-preemptive OS. We'll see. So basically what I'm going to do here is just a really lightning tour through these three systems. Don't worry if there might be a little bit of stuff you don't understand, but just kind of sit back and get an impression of the system. All right, let's go into Knock for a second. So I sometimes call Knock a functional assembly language. You can program in Knock, but there are no symbols or anything, so you're typing numbers and doing tree geometry by hand. Very much like writing assembly language. You could, but you wouldn't want to. It's basically, it is a Lisp in a sense. It's a Lisp without any of these high-level tools. How do you get symbols out of a Lisp? Well, maybe it's not a Lisp. Key point, no cyclic data structures, no laziness, so no infinite data structures. You cannot, Knock is an interpreter which cannot create cycles. I think that is basically very much the right choice in the modern world. No tracing garbage collectors, kind of nice. If you also remember, this is a persistent system, and if you look at persistent systems, any kind of database, whether it's NoSQL or SQL, basically you'll see acyclic data structures everywhere there. You will not see very many successful databases that use cyclic data structures. It's also, if you're sending data over the network, how do you send a lazy list over the network? How do you send a cycle over the network? You can. It's a little bit harder. And so this is definitely very much designed for kind of the network edge, obviously. It should be extremely efficient. We'll get to how that works in a bit. It should fit on a t-shirt. It should be obviously perfect. I believe that actually I've hit these points. So concepts in Knock, quick. So a value in Knock is a noun. A noun is basically our version of S expressions. It's S expressions without the S because basically all that stuff has been stripped off. Lisp essentially, I would say, has almost kind of a dynamic type system for atoms, which you need if you don't have another type system on top of it, because how do you print an atom? Well, if you have a type system, the type system will tell you how to print the atom. But if you don't have so basically an atom is just an unsigned integer of any size. We use this, an atom will be a number, it could be a string, it could be a network packet, it could be a giant file. It's a blob. But a blob as a number, not as a blob and as a number, and this is how long the number is. A cell is an ordered pair of any two nouns. We don't do pointer comparison. We don't do this. This abstraction is completely semantically opaque. Knock itself is a function from two nouns or a cell of nouns, a subject and a formula to a product. Subject is the data. Formula is the function. A product is the result. And the way we define Knock, we define errors as non-termination. So errors are basically anything that produces bottom. Obviously, we don't do that in practice, but that's how we define the function. So let's go over this spec. We'll see the Knock spec in 2 slides. These are reduction rules. You see 4 basic operators here. The first one is question mark, or as I would say, what. This is a deep operator, so is this a cell or it's an atom? If it's an atom, if it's a cell, it's 0 meaning true, and if it's an atom, it's 1 meaning false. 0 for true, 1 for false. Probably a decision I might do differently next time. But it's morally right and it works. We can also increment an atom. That's our only arithmetic operator is increment. And you see if you try to increment a cell, it reduces to itself, which means an infinite loop, which means an error. You can test for equality, same thing. You can't test for an atom for equality. And the only interesting operator here is this slash, which is a slot, which is a tree addressing scheme. So in this tree addressing scheme, basically 1 is the root of the tree, 2n is the left child of any node, 2n plus 1 is the right child. So basically having this kind of simple tree addressing built into the fundamental interpreter is what lets us not have to deal with scopes and environments and basically all that jazz that we know and love from Lisp. So that's all higher level stuff. All right, so this is the rest of the Knock spec. This is a complete spec here. So the first reduction rule here is kind of interesting. This is something I call autocons. So basically if you have a Knock formula, either the head of that formula, the formula is always a cell, it's always a pair. The head of that formula is either a cell or an atom. If it's a cell, then what we have here is a pair of 2 formulas, and the semantics of that is consing those formulas. So basically you can build up, cons is essentially an implicit operator in a way here. You can build up, you just, glom formulas together and you get this kind of automatically cons thing. Otherwise, so if you see A here is always the subject, and then we're pattern matching in the formula. This, by the way, is not the syntax for anything. This is just pseudocode. Obviously, if you're writing axioms at a certain level, they're written in English. So if the first, if the head of a formula is a number, then if it's well formed. Otherwise, you see down at the bottom, anything that's not well-formed resolves to itself, again, an error. If it's well-formed, we have instruction 0, which is just the slot operator. So that lets us basically pick out a subtree of the subject. Then 1, constant. 2 is eval. So basically, B and C here are formulas against the current subject for a new subject and formula that we're going to evaluate. Again, pretty straightforward. 3, 4, and 5 are the deep, bump, and same operators that we've seen before. Depth test, increment, and equals. Those are actually all the operators that we need for Nock to be as expressive as it wants to be. So we could actually throw away 6 through 10 completely and have a much shorter, cleaner spec. There are simpler Turing-complete interpreters in this, certainly. So, this is intended to be a practical Turing-complete interpreter, and it is actually practical, believe it or not. And you probably don't believe it, so 6 is, I'll leave it as an exercise to the reader if you can figure out how these macros work, but 6 through 10 are all macros. 6 is if then else. 7 composes 2 formulas. 8 composes a formula with the cell of the product of the formula. It's basically declaring a variable. Essentially, you're putting a new value onto that subject and then using it for the next formula. 9 is essentially implementing what whom will use as a function call to be to simplify it enormously. And 10 is a hint. So you see 2 10s there because you can have a dynamic hint or a static hint. What a hint is in this environment is an instruction that throws away data. So if you discard data, basically you're saying to the interpreter, do whatever you want with this data. Do something with it. Hints are anything like a debugging printf is a hint. You're like, I don't know that a debugging printf happened, but if you want to make it happen, make it happen. Memoization, there's a memoization hint. That's another good example. So the hint basically doesn't change the formal result of the computation, but it helps the interpreter do something interesting with it. So that's all of Nock. Now let's. Here's a little example. So Nock, of course, the only integer operation is increment. So if you want to decrement, well, that's a little bit of a problem. You actually have to write some code. You're going to actually have to count up to n-1 to decrement. Not a big deal. Very simple algorithm. So here we're jumping ahead, and on the right side of your screen, basically, you're seeing some Hoon. Those are 2 basically kind of alternate syntaxes for Hoon. One of them is a keyword syntax, which you can probably read just by looking at it. The other one is a rune syntax, which you probably can't read, but that's what we actually use in practice. It's kind of training wheels, no training wheels. And on the left is the actual Nock formula that we generate from this. If I had a couple more hours, I would actually go through this formula, but as it is, it'll just have to serve as an example. All we're doing is we're basically saying, okay, we're going to call the subject A, because that's the number we're decrementing. We're going to add a counter, which is 0. We're going to loop, and we're going to count up to until the increment of B is A. If that is true, our product is B. Otherwise, we're going to loop again with B changed to the increment of B. Pretty straightforward decrement, not super hard. But that kind of brings up a problem that you might think of, which is, O of n decrement. Well, if you try to boot Urbit with a completely naive interpreter, it will immediately start decrementing and keep decrementing until pretty much the end of time. So that's clearly basically a non-starter. There's a well-known solution to optimization problems of this kind. It's called a sufficiently smart interpreter. All your interpreter has to do is simply recognize that it needs to analyze the algorithm that it's interpreting, recognize that it's a decrement algorithm, and implement it efficiently accordingly. We also need to recognize add, multiply, and all other interesting functions. So if you know anything about compiler theory, you know that this is a very hard problem. Fortunately, there's a much easier problem which is related to it. We don't have to recognize every decrement. We just have to recognize the one that we actually call, which is the one in the standard library. Basically, the way we optimize in the system, and this should be sort of compared to, let's say you're building, you're using Java or using Python. What you do, is you say, okay, I wrote some pure code. It's beautiful. It's fast. And oh, it's not fast enough. And I guess I need a native method. So then you call it to C. You rewrite your inner loop or whatever in C. You throw away the original pure code. There's another great advantage, which is that your inner loop in C can make system calls. So it can modify the file system or something. That is not necessarily a very functional way of proceeding. The way we optimize knock and hoon is a little different. So we basically say, when you write, say, decrement, you say, okay, I'm going to declare this in a namespace. I'm going to say to the interpreter, I believe this to be decrement. It's just a conventional name. This is decrement. The interpreter is like, oh, he says this is decrement. Is this true? Well, gee, I'm built to recognize literally, with the hash of the formula, I'm built to run this specific formula efficiently. So I'm going to match this, which is a slightly hard problem, but not a super hard problem. I'm going to match this at runtime, and then I'm going to do the efficient decrement. So the advantage of this approach, there's a number of advantages of this approach. First of all, you have both those routines, the fast decrement in C, which is totally an implementation detail, and you're separating mechanism and policy there, essentially. So you have your fast decrement in C, and then your essentially executable specification of decrement, and you're basically binding the two together. So obviously there's no, you can test these against each other at runtime if you choose. There's certainly, you can sandbox your jet, so it has no reason to make system calls. You can also extend this up the stack, quite a ways. So, for example, we have one of the, we serve our own website using Urbit, and one of the, we serve it from Markdown. So we have a Markdown parser written in Hoon. Well, it's a decent Markdown parser. It's maybe not the world's fastest. Fortunately, Markdown is a standard for some values of the word standard. We basically jet that Markdown parser with an efficient common mark implementation in C. Or, for another, example is Google has this lovely library called TensorFlow. They recently announced that basically they built an ASIC for TensorFlow. I don't know how exactly the programmer talks to that ASIC, but I'm sure it's a mess. What you actually want to do is basically say, okay, I as a programmer am using TensorFlow of this version. I run I declare that this is TensorFlow of a certain version, and then my interpreter is like, aha, I have a chip that can speed up TensorFlow of this version. I'll just use that. And so that scales kind of to in more interesting ways than the, let's call it to C, model scale. So we also use it, by the way, to virtualize knock. So there's actually a virtual knock written in knock if you thought knock was slow. But basically, you can get unlimited levels of virtualization pyramid by basically just recognizing that you're running your own virtualizer and just saying, hey, we're at 6 levels deep. So that's an improvement as well. All right, we're done with knock. That's knock. Pretty cool. Let's build Hoon. Hoon obviously needs to compile itself to knock. It needs to be a pure, strict, higher order type functional language because that's the hotness. It needs to have, I believe it needs to have a simple transformation to knock. So I'm really a Unix and C guy. I'm not a functional programming guy at all. And actually don't know any of their functional languages. So that sort of simplicity, that feeling that basically the compiler is doing something very simple for you is really like a wonderful feeling when you're working inside C. Like you're seeing the system basically at 2 levels. We definitely want a system that doesn't require people to have a math degree. That's a subject of complaint. I think more generally, one of the things that languages like Haskell do is they're functional programming languages, and they encourage you to use these powerful tools as kind of much as possible. Hoon is kind of the opposite. It encourages you to not use these tools. It's basically like, okay, the power is there if you need it, but bear in mind when you're using this kind of functional power, you're imposing cognitive overhead on the ordinary programmer because we really want, this to be something that a Python programmer can pick up and program in. I think the ability to basically teach people these, higher order constructs is, really debatable. I don't think it's proven at all. There's another thing that often happens both with macros and with kind of advanced functional languages where you get into this kind of DSL pattern where basically you're so higher order, you're so meta that every file is written in its own language, which basically gets you to write only code, and that's like a kind of serious downside of functional programming. And the thing is, Hoon is still basically almost as expressive as Haskell. It has the equivalent of type classes. It has genericity. It's like it's not Haskell. Haskell people will be a little disappointed in it, but it's definitely not Lisp. Okay, so let's go a little more into detail on Hoon. So basically, the back end of Hoon is extremely simple. So type inference and code generation together, 1,500 lines of code. Shouldn't be super hard to learn. So where basically Nock is doing subject and formula to product, of course in Hoon we have an actual expression that is written in for some values of the word user level code. The experience of programming without an environment or without a scope or without a heap or without this sort of extra piece of state where you just have the subject is just one noun and everything that you need is in the subject is sort of somewhat unique and different. You keep sort of reaching for that, there must be something that has my variables, but no, there's really just one noun that you're defining a function against. So when we basically take a type system and layer it on top of Nock, we're basically computing a mapping from a type and an expression to a type and a formula. So we have input type or subject type and expression turns into product type and the Nock formula that computes that expression. So again, a very, very simple, straightforward kind of relationship to Nock here. The inference algorithm is extremely stupid. It infers only forward. It does not use unification at all. It can infer tail recursion, but not head recursion. So a general pattern is you need a few more sort of casts to help the type system out. It's still a strict type system, but you need to help it a little bit. My view is that basically having a stupider inference algorithm is again a UI win for a language. Because basically when you program in a language, you kind of need to follow what the compiler is doing. The more powerful the algorithm you're following, basically the harder it's going to be for people to follow. And so, when I look at Haskell, I see basically kind of two kinds of Haskell users in a way. I see people who treat Haskell as a black box and are like, it's sort of a learn you a Haskell kind of way. And they're like, oh, I made it work, cool. And then there are the people that actually understand the math. And kind of both of those, kind of situations don't scale in a way. And so having a simpler system is definitely, I think, a win. So a little more about Hoon. This has brought us in for some criticism, but Hoon basically, since it sort of has its own way of doing things, we invent a lot of terms because basically the ordinary terms tend to be confusing. So, and we also have a four-letter name kind of convention going on. So an expression or an AST is a twig. A type is, well, there's actually three things that are basically correspond to a type. So a type as in sort of a set of nouns and a semantics ascribed to them is called a span. A type in terms of a constructor is called a mold. And then we also have basically at the kind of OS level, I don't think I'll get into that today, basically the equivalent of MIME types, which is something else also entirely. Looking at molds, basically Hoon is a pure prototype language. There's no syntax for defining a span. The only thing you can define are twigs. So when you want to define basically a span, a range, a type in the usual sense, a set of nouns that you're interested in, what you define is actually a normalizing function that takes an arbitrary noun and produces a noun of that type that you're interested in. What's kind of nice about that is that basically if this is the way you define types, anytime you define a type, you've defined a validator for untrusted network data. So we do a fair bit of validating untrusted network data in today's environment, so that's kind of a win. Basic concepts of the type system. This is almost a complete definition of the Hoon type system. It's missing a little bit of stuff. I'll see if I can fill that in, but we got to move pretty fast here. And I'm not going to talk about twigs at all because once you understand basically a data representation, it's pretty straightforward. So a span defines a set of nouns. What can the set be? It can be noun, which means it could be any noun, any, remember, S expression basically. It could be void, which is an empty set. I'm going to skip over atom and core because I have separate slides for those. A cell, obviously a cell. Here's the span of the head, span of the tail. A face, basically, we're going to label this span. And so remember that there's no symbol table, there's no anything in here. So the labels actually live inside the type. So when you're searching for a label, you're actually doing a depth-first search of basically the type of the subject. Fortunately, computers have gotten a lot faster. You can cache this. We do cache it. But, I mean, fine. It's a depth-first search. How big is your subject, right? You can have a fork, which is a union of spans. Pretty obvious. And the only really interesting one on this page is hold. So basically, one thing we never do in this system is we never calculate type signatures. So this is a strict system. We can't do laziness. What hold means is basically the span here is the result of if you take subject P and run expression Q against it. So this is very much manual laziness. Manual laziness has some nice benefits. Namely, you can use this as you can use a manually lazy span as a key in a key value data structure, which is pretty difficult with infinite data structures. So that's basically, those are the simple ones. Let me get to the non-boring spans, atom and core. So atom is just an atom. Slightly non-boring in that you can say this could be any atom or you could say this could be a constant. So the unit there is Hoon's equivalent of maybe. And so, if that's set, then we have, this is just a constant atom. Then we have P there is something interesting. The term is a symbol, essentially. And we have what I call an aura. This is a soft type. This is a basically non-enforced type or enforced gently type. And if you remember, Lisp, of course, has this dynamic type in its atoms, which is just really awful in my personal opinion. And if you have a type system, basically the type system, when it has an atom, needs to be able to describe how do you print this atom. Gee, what happens if I try to use a furlong as if it was a fortnight? What happens if I try to use an IP address as if it was a string? All those are atoms. And so you basically need to label those and describe them kind of informally. And there's a basically a system of specialization simply by the length of the name. So you can basically text, ASCII text with a symbol constraint. All these are informal conventions. None of them there's no dependent types in the system. Sorry, yet another no dependent types. They're not enforced at all, except that basically, if you want to turn an IP address into a string, basically, and be so foolish, you have to manually tell it. You have to cast up to just a raw atom and then down back to your string. So you have to work to basically screw up that way. That's an interesting design. You don't usually see a soft type in a functional language. I think it's worked pretty well. It's not perfect. I think the most interesting span, and remember a span is describing a set of nouns. The most interesting one is core, which is essentially an object, or it's an object sort of in a very broad and general sense. It's actually the general case of objects and functions and a lot of other things which you don't really have a name for. A core is a cell. The head of the cell is a battery, which is either one formula or a tree of formulas. Remembering a formula is just a knock function. The tail is a payload, which is basically any noun. When we run the arms, which are basically, they're not methods, they're computed attributes in the battery, we run that with the whole core as the subject. So we basically have this thing that has a bunch of code in it. It's like, you can think of, if you know C++ implementation, you can think of it as like a vtable. Right, and so here's a vtable with a bunch of formulas in it, and you say, I want to get foo out of this core. It's like, oh, great, I have a foo. I'm going to basically calculate, that's going to resolve to this calculation. So there's no separate namespace for basically data and for code. So if you're looking for foo on a core, and the core doesn't have foo, there's no foo in the battery. Then it goes in and says, oh, well, let's look in the payload. Let's descend down the tree. Notice also, again, that there is no attempt to create a type signature here. So this is just a map of a term to the twig. Twig is a source. That's a source expression. So basically, and that's in the type. So when I call foo on this core, I basically go in and I say, well, okay, that's going to generate one of these hold things. So it says, okay, the type of the span of the result of this foo is basically the core type and the twig. And so when we actually evaluate that, we have to basically manually work through the laziness and say, oh, well, what's in that type? Gee, I don't know, let me calculate it and find out. That actually, that works rather well. Okay, here's some advanced theory. I'm going to go over this super quickly. So hold, again, is manual laziness. One of the nice things about it is that basically you can build a conservative work list algorithm. Let's say you're building a linked list. Let's say you want to do a type comparison on 2 linked lists. Okay, now this is basically, this is a structural comparison. So you're saying, these could be totally different definitions of linked list. Do they match? So if you basically traverse this span, what you're going to see is that traverse repeats itself. And because it repeats itself, you can say, gee, I already checked that there were no violations on this arm, on this branch, so I'm going to call that fine. And that's basically how you can do sort of type logic in this manually evaluated space. Again, very, very stupid. If you ask, any smart undergraduate could come up with this scheme. At a little more depth, I'm going to go over this super quickly. You may not understand it. Basically, in polymorphism, you have two, a lot of different kinds of languages, and I'm thinking of like Eiffel and like the Bertrand-Meyer kind of world of languages have basically 2 kinds of polymorphism. You have variance and you have genericity. So basically, any polymorphism in any system like this is about basically if I change a core. Let's say, okay, I built this core, I stuck this battery on this payload, but now I changed the payload. Maybe I changed the payload to something of a different type. Can I run this core? So basically, can I run this ARM, or will it just be a total disaster? And that question is actually answered when you try to run the ARM. So, there's a, sort of simple question of variance, basically. Can I use this one payload as another payload? The way we do genericity is, I can, sort of explain this intuitively at a very high level. When you're doing genericity, you're basically saying, when you're doing variance, you're basically saying, okay, does my mutated payload work like the original payload? When you're doing genericity, what you're saying is, okay, I've changed the type of this payload. I've changed it to something totally different. Now I'm going to run this ARM on it. I'm not going to recompile this ARM. I'm going to run the original knock formula that was calculated for something of a totally different type. And the question you have to answer is that going to work? And what span is it going to produce? You're basically treating the twig, you're treating the ARM as a macro and essentially working through it. So it's like the classic example, can you build a function to swap 2 things of an arbitrary type? So, you basically do that with genericity in Hoon. So that works. That's how we do containers, all the usual, jazz. And it's essentially kind of this like ghetto low rent way of doing type classes. Syntax design. Let's go into the syntax. Hoon has a very unusual syntax you've seen already. A lot of people think it looks pretty gnarly. There is a reason for doing this gnarly thing. The reason is that basically there are kind of 3 problems that you see in a lot of functional languages that are syntactic problems. One problem is that basically expressions slope downward and to the right, and so they keep attacking your right margin if they get too complicated. In a procedural language, you've got this nice division between statements and statements flow down and expressions flow across, and it gives you this kind of nice tree-shaped structure, which lets you work within an 80-column margin. In a functional language, you often don't have that, and so you get this, kind of slanty thing, which is uncomfortable to work with. Another problem in syntax that a lot of these languages have is they have this unpleasant choice between, am I going to have 17 parentheses in a row, or am I going to do significant white space? Both of those they work, they're just not super pretty. Another problem that I don't know if everyone has this problem, I certainly have this problem when I look at Lisps and a lot of similar things, is basically I can't distinguish special forms from symbols. I can't distinguish, is this part of the language, or is this something that somebody included from a library, or is it a macro? And basically making that, again, getting away from this sort of pervasive DSLization is definitely a goal of the system. Speeding up a little, so before showing the syntax, basically a twig structure, once again, the twig is a Hoon AST. You can Hoon has the same kind of autocons feature that Nock does. So basically, cons is assumed. If you basically make a cell of 2 Hoon twigs, that's a cons. In general, as opposed to Lisp, Hoon is kind of more pair-oriented and more tuple-oriented. We don't throw in terminators everywhere willy-nilly. That's kind of more appropriate for a typed system, I think. Most twigs are tagged unions. So they have a head, which is a stem, which is a symbol, and a bulb, which is, the tail, which is totally dependent on the stem. It's usually a tuple or a list of twigs, and let's see how that works in practice. So basically, there's a regular form. Again, most bulbs are tuples. Some are in area, and there we do need a terminator. But what we do is we basically have two regular forms of syntax, one which sort of looks like an expression and one which looks like a statement. And so those two ifs there are the same code, but they look a little different. And what you do is you basically build these, a structure whose backbone is basically tall twigs, and then a tall twig can contain a flat one, but not vice versa. So basically, you're mimicking the kind of structure of imperative code that has this kind of statement expression duality, but it's all an expression. There's no imperative anything. Another thing that you're doing basically to control the right margin here, what you really want, you'll notice that C is at the same indentation as the if there. So basically, you want to lose no space basically for your largest. Hopefully C is the biggest branch. C is not the biggest branch. You want unless instead of if. But basically, you really, as a programmer, there's sort of an art of arranging these things, and you arrange them so that they flow down and not across. And it becomes very easy to read once you know it, like any language. And here's the funnest and most fancy part of our crazy syntax. So first of all, you've got regular forms and irregular forms. So in a regular form, arbitrary syntax, at least it's always flat, but that's just something you have to learn. One of the things I feel, if you look at the implementation of the Hoon compiler, what you'll see is that basically the front end is actually as big as the back end, which is really quite unusual. And that's because basically as a human being, you've got this great hardware for basically parsing. You don't have hardware for type inference. So what we've done is basically the keyword form that you saw. Remember you saw those two forms of Hoon, one using keywords and one using runes. I'm going to step forward and show you. Here are two forms of FizzBuzz. On the right, you see runes. On the left, you see keywords. Stepping back for a second, to make these basically pronounceable, what we've done is taken every ASCII character and given it a single syllable name. So where if you see if here, so if is the colon prefixed if there. That's also the symbol that's actually in the physical twig. You can also, as a syntax, you can say question colon. I wouldn't say question colon, though. I would say wet col, which is a lot faster than saying question colon, not to mention ampersand. So basically, everyone who's learned this is like, why doesn't everyone know this, and why do I have to say tilde to like my normal friends when I could say sig? Hopefully it'll catch on. If it doesn't catch on, at least it's useful in Hoon. So if we go back to this and we look at the right. You would say gate in fast atom, or you would say Bartiz in fast atom for the start of that. Let me give you 20 seconds to just observe the fizz buzzes here. I think that the one on the left should be at least pretty readable. Okay, so that's Hoon. Let's move up to Arvo. Now we're at the operating system level. The kernel of Arvo is a Hoon core, and this is basically where we get back to our transition function. So this core basically has a very fixed battery structure. You can think of it as basically like a V-table with a fixed structure. And the Unix interpreter talks to this core basically at the knock level. In the lifecycle function, it's defined at the knock level. So you basically just hard code those formula offsets. You can just fix that because you have only a few functions there. So basically, this is how you have a system that can completely upgrade itself because, again, the whole lifecycle function is defined entirely in knock. And basically, let's say you get an event, and that event is actually a source code update in the revision control system that gives you new source code for Hoon, the language itself. As long as your new language can build a core that is shaped like the ones that your old language built, you can turn Hoon into anything. So Arvo is actually a very, very simple system. It's only a few hundred lines of code. It probably should be less than 600, actually. What it does is it does sort of an internal event cascade. So you're all familiar with, like you get an event from the outside, and then you're like, this happened internally. Event systems that are very complicated and deep like this one very quickly turn into spaghetti event logic. There's a duality between events and procedure calls, in which basically an event is a transfer of control, essentially. And if you take that duality simply, the dual of a simple event system is goto. So basically, when you have, you're like, oh, throw these events, and then it's like the system will go here, and it will go there, and it was like, why are you doing this? So essentially, we have what you might call the equivalent of go sub. For anyone know BASIC in this room? Anyone? Wow, that's awesome. I don't feel so old now. You have essentially the equivalent of subroutines in an event kind of model, and you have basically this kind of causal model, which I don't want to get super into, but definitely if you're building JavaScript event frameworks, I think you could use something like this. It also has a global type referentially transparent namespace. So basically, use any data in the world as if it was a typed constant. That's kind of nice. Most of the work of Arvo is done by what are called veins, which are essentially kernel modules, and they have essentially the same kind of core-like structure as the Arvo core itself. So these are loaded from source, obviously at runtime. Let me just run through a few of the things we do. So encrypted packet networking, we'll talk about that in a sec. Timers, obviously. Clay, which is like a typed Git. Console, obviously. Air, we'll see that hopefully driving a demo in a second. A functional build system, I don't really know how to describe that. And an application engine. And the applications, again, are cores within Gull. So you have sort of these kind of multiple levels of virtualization. When you're running user-level code, you're actually running it in a virtual NOC. And that virtual NOC has an extra instruction. It has an instruction 11 that dereferences the basically global namespace. So you're really like dereferencing the whole world as if it was a constant. Again, that due to the way NOC works, you can basically virtualize at any depth of virtual interpreters without any real cost, because you're actually in the implementation just setting a flag. All right, that's a very, very broad overview of Arvo. Let's go back to the top and basically look at what Urbit is doing at the top level. So we're sort of back to the user level here. There's fortunately nothing else in the stack besides Nakun and Arvo. And at the top level, what users really see the most in Urbit is the public key infrastructure, kind of the identity model. Basically, one Urbit is one event history, it's one state, it's one instance, and it has one identity. And we basically establish that identity when we're booting the Urbit. What exactly is this identity? What does it mean? So basically, again, the great thing about doing things from a clean slate is you really get to think from scratch, which is kind of neat. And one thing about networking that is done kind of in the internet certainly, is you have these two levels of, well, that gets better audio. You have these two levels of addressing. So you have IP addresses and you have DNS. And the DNS is human meaningful and IP addresses are routable addresses. So in Urbit, this is compressed into one layer. So you actually have one layer which is both a human memorable layer and it's both a routing address and a name. And it's actually your personal identity as well. It's also the base of a path in the global immutable namespace. So there's a problem called Zucco's triangle. Does anyone in the room know Zucco's triangle? Ooh, we're definitely not in network land here. That's fine. Zucco's triangle basically says there are three things that you want out of an identity system. You want the names to be human meaningful, you want them to be secure, and you want them to be decentralized. And you can get only two of those three things. So Facebook, secure, I hope. Human meaningful names, definitely. Decentralized, not at all. BitTorrent, decentralized, yes. Human meaningful names, no. And so there's basically a problem there that, as an OS guy, what they teach us to do is find the trade-off and almost solve the problem. So the trade-off that we make here is basically the trivial solution for an identity system of this scale is basically to say your identity is the hash of your initial public key. Very easy. IPFS uses this. Very easy to do. How do you remember a 128-bit hash? You don't. And so what we're looking for is basically a way to make these names that are memorable but not meaningful. So first trick we do is we basically come up with a new way of representing numbers. Many things like this have been done before, not super original, but we do a phonemic base 256. So if you look at my three numbers there, there's a hexadecimal number in Urbit syntax, there's a in Hoon syntax, there's an IP address. We also have a syntax for that. And then there's 128, 42, 19, 109 versus Patnub Tarlud. Patnub Tarlud is a lot easier to remember. It's kind of like a human name in a foreign language. People actually bond with these names very easily and very quickly. I'm Tasfine Pardive. I think of myself. People say Tasfine. I turn around. Of course, that's a 32-bit number, which is a lot shorter than a 128-bit number. So how you get from 128 bits to 32 is tricky. So you can actually do the 128-bit hash of a public key thing. That's called a comment. Anyone can create their own Urbit identity. That is a completely non-scarce resource. And it's also, there's just no way of making a 128-bit number, memorable. So what you notice is that basically the most valuable real estate in this is down at the bottom of this whole 128-bit space. And in fact, you can overlay, a 128-bit hash will never be a 64-bit number, so you can overlay a completely different 64-bit identity scheme on the bottom of this. So your 64-bit scheme is distributed hierarchically. It's cryptographic property a little bit like Bitcoin, but it doesn't use a blockchain. So the way it works is that a 64-bit chip is the initial key is signed by its 32-bit parent, basically the half-width prefix. The 32-bit chip is signed by its 16-bit parent. The 16-bit chip, which is a star, is signed by its 8-bit parent. And the fingerprints of 8-bit galaxies are hard-coded in the kernel source. This is what we call pre-mined in the Bitcoin world. Basically, again, this is a PKI in which revocation and renewal are the same thing. So basically, when you want to change a key, whether that's because you want to give someone else this identity, or you just feel like your key might be a little bit compromised, you basically sign the new key with the old key. Unless you're a moon should not be floating around unaccompanied. You sign your own updates. So basically, your parent, signs the first key, but you sign the second. So you're genuinely independent here. The main sort of question in that is basically how these updates get distributed. Fortunately, there's a lot fewer of them than sort of the equivalent, which is like a Bitcoin spend. So it's, there's a lot more room for basically just sort of handling it in a kind of less aggressive way than Bitcoin does. But it's the same basic principle. Your identity is definitely cryptographic property. You own it, you can sell it, et cetera. And there's, the 32-bit point is clearly kind of the right point for human beings. One of the things about having these 32-bit names as your names is basically, like in any situation in which people are actually using this system, some people are using it, but hopefully everyone will be using it, you have a scarcity there. You only have 4 billion. And so the price of this scarce resource cannot fall to zero. So one of the things about that situation is that the basic problem, one of the reasons why my mother can't run her own internet server is that the internet is basically, a digital Mos Eisley. I mean, it's just all kinds of scum and villainy are out there. And when you get a packet from someone, you have no way of ascertaining the reputation of this IP address. Yes, there are IP address reputation systems. In practice, they basically turn off all residential things and don't let them send email. But the ownership of an IP address is not clear. And so you can't really use, an IP address is not property, you can't really use it as a mechanism in this way. When you basically have an address that's a scarce resource, let's say you paid $10 for your planet. Okay, I paid $10. I want to be able to compute. Then you're going to send messages directly from that planet. You're definitely not going to send them through like Google or some MTU, and if you spam, like someone's like, hey, I got a spam from Tasfine Pardive, and you go on a blacklist like this, and basically your $10 is now worthless because no one will accept anything from that planet anymore. So essentially, in order, like, your spam better have made you $10, or like, you know, and that's a pretty high bar for spam. And so basically, just by having this sort of limited supply of real estate that's treated as digital property, you basically have the basis for building a reputation system that works. Because the real killer of reputation systems is an infinite supply of identities. Because you have this problem where you're like, I've never seen this identity before. Maybe it's a new user. I really want to say hi. Maybe it's that spammer I just banned. I really don't want to say hi. That's kind of an unsolvable problem. And so basically, I think this is one of the things, like, you know, nobody, a tiny young network like Urbit, nobody abuses. But, you know, in the future, as you grow, basically you become a target. And so having a system like this helps you not be a target. Let's fall back on the point of all this. Inventing new system software is always a bad idea. It's a terrible, terrible thing to do. Never, never, never do this. So let's go back to basically the goal of this project, which is to build a personal server. So a personal server is going to be a social server. So if you have a real personal server that's a real social server, when I socialize with you, in the ordinary case, barring like weird identity games, I should be sending packets directly to you. I shouldn't be sending packets to some Facebook thing over there that then sends them to you. I should be able to basically actually socialize in a distributed way using distributed protocols. And one of the things about the way we compute today, and the reason basically we don't do this, is that if you look at the difficulty of distributed programming, let's say you're building like a tic-tac-toe app, compare the difficulty of building distributed tic-tac-toe with the difficulty of building centralized tic-tac-toe. Centralized tic-tac-toe, you know, my score, your score, they're variables. They're in the same, you know, data structure. It's easy. Then suddenly you're building distributed tic-tac-toe and you're like have to apply to the IETF for an RFC for your TTTP, right? And, you know, it's just like 6 orders of magnitude different in difficulty. And like, if you want to ask why we don't have a decentralized internet, basically the reason we don't have a decentralized internet is that decentralized programming is too damn hard. So basically, you need to solve this problem if you're going to build anything like a true personal server. So let me talk a little bit about the kind of programmer experience of, you know, where we're aiming to get with this. This is actually my next to last slide. So let's see. First of all, you're programming the system. You can dereference a global immutable namespace. So basically use any data in the world as if it was a typed constant. That's kind of nice. Your application state is permanent. You don't need a database to basically flush stuff out to when, you know, for your data actually exist. When you do an update, your updates basically come through reactively through the, you have basically a revision control system. That's Clay, or I didn't talk much about that, but it's basically a revision control system with hooks. And so you're like, oh, I got a source code update for this thing I'm running. Then I'm like, oh, I need to change out the code. Oh, gee, the type of my data changed, so I need to have a type adapter in there to make that work. That all works great. A very different experience from kind of updates or upgrades in a lot of systems. When you get to messaging patterns, basically, you've got a poke, which is a forward, basically, essentially an RPC without a return, and you've got a subscription model. Let's look at basically what we get with pokes for a moment. Number one, you get exactly once delivery. You've probably heard that exactly once delivery is impossible. There was a great blog post about that a few months ago. Exactly once delivery in message semantics actually is possible if all of your entities are single level stores and if they can basically run permanent sessions. So you have a permanent session and you're like, oh, I expect, you know, message 7 from you. Well, you're only going to get message 7 once. Where that breaks down in this kind of system where you have transient and permanent state is you reboot the computer and then you're like, do I expect message 7 or message 6? Or, you know, you have these, idempotence problems. So every message is a transaction in this kind of distributed programming environment. If the transaction succeeds, there's no return data. So it's a one-way transaction. Your messages are automatically type checked and validated on the receiving side. You can even do basically protocol type updates on a live network and not propagate errors to the user. The data that you get over the wire is passed to you typed. You basically just get it as an argument, and it's a typed value. We do end-to-end acknowledgements, which basically means there's kind of a single error mode. So when you're doing acknowledgements, like think about you're doing a normal RPC over HTTP. Something goes wrong. Well, what could go wrong? Your socket could break. You could get an HTTP error. You could get an error at the RPC layer. What do you even do with half of these things? Like, they're different kinds of error. And that basically is just very, very difficult to handle right. So if you're basically doing acknowledgments at an end-to-end level, that means the packet level ACK that you send back is actually the transaction acknowledgement that you succeeded or failed. Messages are queued by the sender, obviously. This is a P2P network. It traverses NAT. And of course, it's authenticated and encrypted. Your subscriptions are sending diffs. Those, again, are typed. So this is a very different distributed programming experience than your sort of normal, I'm writing this in Node experience. And our experience is basically you just do things and they pretty much just work. What is the status of the system? It's about 30,000 lines of Coon, including basic apps. It's totally open source. You can go to urbit.org, and which is served by Urbit, although we cache it. Yeah, I mean, it essentially works. We run occasional global flag days, so you might not want to move your business onto this system. Yeah, I mean, when you're creating a system like this involves a lot of rewriting stuff over and over again until it actually works right. We're basically getting to the end of that process, and we're kind of close to being ready to sell some address space to the public. Let me do a quick demo of this system to see if it's actually working. I'm actually doing this over my... so here is, you're in Urbit. Are we live? Yes, we're live. That bounced off the server and came back. So that's basically a simple console talk app. Hello from... a little bit slow on the typing there. Our console path is pretty complicated, and we could use some serious optimization. Let me see if I can bring up the web UI of talk. Yes, here is a web app. Let me get it fully up. Looks like it needs a reload, which it actually should not. Hate it when that happens. But here, basically, you're seeing a web UI. Do you want to say something? Anyone want to say something? I'll just be hello from Lambda Conf again. Boulder is beautiful. So, beautiful with an extra K. This has to bounce off the server to get back. Actually, the Colorado's router seems to be blocking my, my NAT transition directly, but I'm doing it via Verizon, so it works fine. The task-find part of it is actually running on this laptop here, so that was a very simple demo. And now, any questions? Yes.
So does Richard Stallman know about this?
I don't think so.
Because I don't think this would really get to what Richard Stallman would like to see.
I think there's a lot of people who are tired of this sort of Facebookization of the internet, and this is definitely also. I mean, is this a Lisp? Is this basically Emacs? At a certain level, it's basically Emacs. All right, we're at a 1 minute warning here. Time for maybe one or two more questions. Bueller? Yes.
So I feel like maybe you're trying too hard to be confusing, where like you use the word twig, but like always refer to it as an ASD.
Mm-hmm.
Is there a particular reason for like these 4-letter Scrabble names?
I mean, the reason is basically you want to use the word that the actual source code uses. Is the reason for that being the convention in the source code? Is that a good reason? Maybe not necessarily. It certainly makes things kind of tighter and more readable in a way. There's an aesthetic there's an aesthetic of short names which works fairly well in kind of a functional environment, which wouldn't work in an imperative environment. The criticism that this is a little more obfuscated than it has to be is certainly one that I think holds a little bit of water.
So when you chat to the one message and it ends up in the browser, how did it go through the centralized event store?
So that is basically if I turn on debugging here, I'll turn on debugging, and you'll see a lot of.
Like where are those packages?
Okay, so what's actually happening is that packet, so I'm logged into, I could log in via taskfindpartarchive.urbit.org. Here, let me turn this off, this is horrible. I could log in via taskfindpartarchive.urbit.org and be proxied by basically the star that is, taskfindpartarchive is a planet of, but basically I'm in a channel, that channel is hosted on DOSNEC, which is the star that I'm responsible to. And so basically that packet is going up to DOSNEC, coming back to me, and then it's going over localhost 8080 to the browser.
Nice.
All right, any more questions? I think we're at time.